Okay, hello everybody. Today I'm going to talk about this paper in which what I'm trying to do is to kind of establish a connection between the possibility of conducting an ideal abstract interpretation, that is a complete one, on domains which exhibit a particularly simple structure. So I'm going to do that through a series of rewriting processes which are semantic preserving. And before I want to start with a little introduction to how the talk will be structured. So I would start by laying some foundations for clarifying what I'm going to use next, and then move towards the first big result of this talk, that is showing that under a certain assumption we can characterize class of programs based on the fact that we can conduct a complete abstraction for which termination is decidable. Then I move on to introducing this intermediate syntax, which is useful to get to the second result of this talk, that is also how to address the problem of deciding semantic equivalence between programs for that specific class, and then discuss a little bit about applicability and of the ideas presented. So to start off, we consider notational semantics. For simplicity reasons, I consider programs with a single integer variable, but these all the arguments can be extended to multiple variables. It's just a matter of not overcomplicating the presentation. And as usual, we have a collecting semantics, acting of sets of states, which in this case it's set of integer numbers. And yeah, here we get to abstract interpretation. So in general, in abstract interpretation, we know that we get a sound over-approximation of program behavior. And when we have this condition, then we have completeness. Now, completeness intuitively is a very nice scenario for analysis because intuitively it includes the fact that no error is introduced at intermediate steps of computation, right? I have a quick example just to show an example of incomplete behavior. So consider this program which computes the absolute value of a number. Then we start, for example, with the set -5 and 7. And if we execute the program, then just as we expect, -5 gets converted to a positive number, and we get this. Now we consider the interval domain, which is not complete in this case, for which the program is not complete. We get as an abstraction the interval 5, 6, and 7. And instead, if we first abstract the input and execute the semantic, then what we get is, of course, a different result. We get that the output is the interval 0 to 7. So in this case, for example, we don't have completeness. So now that these things are set, in general, we know that an abstract domain can have infinitely many elements. And in particular, it can be infinitely wide and infinitely high. But we introduced the notion of a bounded abstract domain. That is, abstract domain for which there is a constant k, which bounds the length of every ascending chain in the domain. This means that if we take any path starting from bottom and going to top, then it will contain at most k elements. Okay? Now, this is the concrete semantics, and we want to focus only on the definition for while loops. And in particular, as we expect, we have the list fixed point definition. And so this can be computed via tiny iterates and so on. The same holds for the abstract semantic, where we have this fixed point, this time on the abstract domain, but it's always cleanly iterated. Now, what happens if our abstract domain is bounded? Then the computation of the least fixed point will not produce more than k elements. And this allows us for us intuitive substitution. That is, we can replace the least fixed point with the kth cleanly iterate. And this allows us to rewrite a while loop in an equivalent form in the abstract domain, which is based on that substitution, and that it translates to unrolling the loop k times, or k minus 1 times. And where in the innermost branch, we have a trivial while loop, which is of the form while true to skip. Then we can apply this process starting with the innermost while loops in our program and moving forward outwards to the other while loops. And this allows us to get rid of every while loop in our program and find one that is, of course, equivalent under the abstract semantic. And it only contains basic comments, that is, assignments, skip comments, or loops of the form while true to skip. Yeah, this is how we define it. And so this is equivalent under the abstract semantic, but suppose that the bounded abstract domain we considered is complete for our program. Then, given that it's also strict, meaning that the bottom element in the abstract domain gets mapped to the bottom element in the concrete, this equivalence translates to the concrete semantics too. Intuitively, we can start by showing that they behave the same in the concrete from a divergence perspective. And from that, we can show that the program is completely equivalent also in the concrete domain. So this is the key to our first result. That is, if we consider programs for which there exists an abstract domain which is bounded and strict, then we have this procedure, which consists of unrolling the while loops in the program and getting a program which is equivalent, for which deciding termination is very easy. Because, of course, you just follow the command. If you get into a while, you're going to diverge. Otherwise, you're not. Okay, this allows us to conclude that if we consider the class of programs for which such hypotheses are satisfied, then this limits the expressivity of that class of program, because termination is an undecidable problem in general. Okay, so given that we have that way of removing non-trivial loops for programs, I am now going to talk about this intermediate representation for programs. If you're familiar with the Dijkstraat command, this is very similar, or actually a particular case of that. We introduce what we call select constructs, which are multi-way conditional statements, basically. For example, here we have an if command testing for x equal to 0, which will be a select command with two ways, x equal to 0 and x different from 0. And this is this comes in handy for defining a set. Okay, so yeah, this is essentially the historical commands. The only thing is we require that the guards form a partition of the whole state space. Yeah, so this intermediate representation allows us to define a way to then flatten out the structure of the program, translating it into an equivalent form which is only on one, or the form of one big select command. And this can be done through a set of rewriting rules, which are the following. Intuitively, they allow to move one command which occurs after or before a select command inside of the branches, merging sequentially composed select commands or nested ones. They're kind of intuitive the least intuitive one is for the precomposition with a command, because we want to move a command C occurring before a select command inside each of the branch. But in order to do that, we need to update the guards. And updating the guards requires what we call an inverse semantics. So if we take a set S of states, that gets mapped to a set S prime of states by the semantic of C, and the inverse semantics applied to S prime gives us the biggest set, which will be mapped back to S prime by the semantics. And this is useful for updating each of the guards in the select branches to ensure that the manipulations are semantically preserving. Okay. So, given these 4 rules I talked about, we define what we call a select normal form. That is, our program is in select normal form if it contains at most one select construct and no other command occurring before or after that. So it's either only one select construct, or it doesn't have any select construct in it. Then we move forward, and we also define what we call reduced select normal form, which, in addition to the previous points, it also requires that no sequential compositions appear in the program. And this can be done because, as I said before, we have what we call basic commands, which are just either a while true to skip command, or an assignment, or a skip command. And we can merge them together. Intuitively, skip can be just removed. While true to skip loops just absorbs everything else appearing before or after them. And assignments can be merged syntactically by substitution. And then, okay, so the idea is, if we take an initial program, we unroll every loop, we only get trivial while loops remaining. We translate it to select form, reduce it to reduced select normal form. And then if we do that to 2 programs, for example, such as this one, we are left with 2 reduced select normal form programs. And now I'm going to show how we can compare them in order to establish if they are semantic equivalent. So we iterate over pairs of branches, and we consider every pair composed of one branch from the first one and one from the second one. And intuitively, what we want to do is build a set of formulas in the form of implications such that they ensure that if an execution executes these 2 branches we are considering, then it will behave the same. Intuitively, if the conjunction of the guard holds, then the 2 corresponding commands will behave the same. So this can be done very easily because we have a limited set of basic commands. So for example, here, cbottom is a shorthand for while true to skip loops. They are obviously equal, so the implied part is true. So yeah, we can just discard that. Then if cbottom is compared with skip, they will never be the same. So we just negate the premise. And so on and so forth. We can iterate these over all the pairs, and we're left with a set of formulas, which leads us to our second result. That is, if we take 2 programs for which there exist abstract domains which are complete and bounded, we can apply this process of removing non-trivial loops, translating, and all of that, and then compare them following this approach. And we find that the 2 original programs are semantically equivalent if and only if this set of formulas we obtain in this way are all valid. Yet again, this also gives some insight on how to attack the problem of semantic equivalence, which of course it's not easy in general. Okay, so Now, I'm going to talk a bit about applicability of the ideas which I've shown. And in particular, a case of bounded domains is that of Boolean abstraction domains. For those of you who are not familiar with it, if we consider a set of predicates P, so P1 to Pn, those are predicates, Boolean predicates defined over states, then we can define the Boolean abstraction domain bool of P as this. And so, for example, we consider these three predicates, checking if a number is even, if it's positive, less than 42. And for each of the states sigma, we can get root values for each of the predicates. Then we substitute them with 0, 1. And what we get is that for each state, we can obtain a bit vector. Okay, then simply the abstraction of this set of states is this set of bit vectors. And conversely, the concretization function mapped to this set of bit vectors is any state which satisfies at least one of these bit vectors. So this case is interesting because bounded domains defined this way are essentially power sets of a set of bit vectors, so they're obviously bounded since the number of predicates is finite. And so obviously if you take the union of two sets of predicates, that is also bounded. Now, it is known that completeness can be studied in a compositional way, meaning that if we have a program such as this one, then we can check for each of the guards, and if a certain abstract domain A is complete for each of the guards appearing in the program, meaning that the corresponding filtering function is complete, and that domain A is complete for all assignments appearing in the program, then we can conclude that that domain A is complete for the whole program. This is interesting because if we put it together with the Boolean abstraction domains, then it is easy to see that if we consider a Boolean abstraction domain, then all guards checking for predicates over which the domain is defined are complete. And moreover, if we have a function f which is complete over both the Boolean domain over set P and the Boolean domain over set Q, then that function will be complete also over the Boolean domain over the union of the two sets of predicates. This suggests a general idea for trying to reason on how to synthesize an abstract domain which is bounded, strict and complete for our program, reasoning in a kind of modular way. Meaning that what we can try to do is to obtain sets of predicates P1 to Pn, each tailored to one part of the program and to the guards appearing in that part of the program. Keeping in mind that we want that each of the Boolean domains over these sets of predicates P1 to Pn need to be complete for all of the assignments. And then we can take the union of all of these sets of predicates, and this ensures that the resulting Boolean abstraction domain is complete for the whole program. So this is just a way to reason locally on guards to synthesize such a domain. And this leads us to some funny corollaries, such that if we consider programs which only test for example, modulo congruencies, and which only use arithmetic operations, meaning plus, minus, and multiplication in assignments, then it is easy to synthesize Boolean abstraction domain for each of the modular congruencies. They will all be complete for those operations. So we can conclude that termination is decidable for any of for that whole class of program. And also semantic equivalence is easy to check. So summing up the whole presentation, we have introduced a way of trying to characterize the expressivity of a class of programs by the possibility of conducting a complete abstraction on domains with specific properties. And also it's interesting to note that we don't really need the full specification of the abstract domain for this whole approach to work. In particular, we only need to know that such a domain exists and the k constant which bounds the height of the domain. We don't really need to implement an interpreter or to even know the structure of the domain. And yeah, we also suggested a way to synthesize following a kind of modular approach domains which are useful for this. So obviously this was very, obviously this was very high level. There are a lot of details and you can check them out in the full paper. So yeah, thank you.
Thank you, speaker. Questions?
So first, very important question. How did you make the slides?
PowerPoint.
Really?
And a lot of more transitions. Those are the key for animations.
We have to talk later. So I'm interested in termination, and so you showed how to synthesize such a bounded abstract domain, right?
Yeah.
But am I correct that the synthesis is only that you present is only if this program itself is already finite state?
I'm sorry,
So
if the program
if all the states of the program are already just a finite set. So for example, if you have modular arithmetic, all the variables can only take up finally many values.
I mean, I'm not sure if I understand the answer, but no, because in general, a bounded domain can be infinite. So yeah, no, I would say no, you don't need the program states to be finite.
All right, yeah, because you have to possibly infinitely many branches.
Yeah.
All right. Okay, I come to you in the break with my question.
Perfect.
Thank you.
The questions?
Hi, thank you for the talk. Have you guys considered other example that is not modular arithmetic?
I mean, for like, you mean for the approach with Boolean abstractions domains?
Yes. Have you guys find anything not modular arithmetic to apply?
I mean, I would. So I don't have an example right now, but I should think about it. But I think that, I mean, modular congruencies are obviously very easy to derive in this case. But yeah, I would need to think about it. But I think that.
Thank you.
More questions? I have an observation or question, maybe. Basically, the select normal form is interesting. If I think of an interpreter is one loop with the selected normal form inside.
Yes.
So basically, your structure seems that removes the external loop of the iteration of the interpreter and simply select few kind of commands that your select normal form will dispatch. This is a way of interpreting your result, or, I mean, of course you're not Turing complete, or you are very restrictive, you decide termination, you decide equivalence, but if I think in terms of what you remove from the universal Turing machine, which is the interpreter, you basically remove the loop and you select very few kind of commands to execute. This is a way of viewing your work.
Yeah, I would say the way is kind of, you're not really removing the loop, you're just kind of conditioning every possible input. So you're, you're removing the loop by kind of flattening the iterations.
Yeah, it's exactly flattening.
Yeah.
Because if I partially evaluate an interpreter with the code that it's going to interpret, and I force the program counter to be dynamic when I do partial evaluation, the result is a flattened code.
Okay.
And the dispatcher choose which command to execute in a loop.
Okay.
You remove the loop.
Yeah, basically, yeah.
Yeah.
Okay. I mean, yeah.
Okay. That's fine. Other questions? Okay, let's thank the speaker again. Beautiful slides.
Thank you.